A military jet once climbed so high that its pilots saw the sky turn black, the earth curve beneath them, and the atmosphere shrink into a thin blue line. Yet it wasn't a spacecraft, and it was never supposed to reach anything close to space. This was a plane built for spying, not for touching the edge of the planet, but its speed, heat, and altitude pushed it into a place few humans have ever seen. In this video, we're going to explore how a Cold War aircraft accidentally crossed into near space, why engineers had to reinvent almost every part of it, and what its pilots experienced while flying higher than missiles could reach. And as you'll see, the truth behind this plane in space is far stranger, and far more unbelievable, than the legend. The day a plane ended up in space. The aircraft was never meant to go to space, but one day it climbed so high that the sky turned black and the Earth curved below it like a photograph from orbit. Inside, the pilot was sealed in a pressurized suit, breathing his own air, far above where normal planes could survive. Was this still flying, or something it? And if a plane shows you the edge of the planet, has it accidentally ended up in space? The night before the mission felt heavy. The crew sat in a locked briefing room with maps spread across the table, maps that did not show city names or country borders clearly because those details were not the point. The point was a route, a straight line across the world at extreme speed. Fuel plans were reviewed again and again, because this aircraft could not simply turn around if something went wrong. Everyone knew too well that once the plane left the ground, there would be no second chances. A few hours before takeoff, the crew followed a seemingly simple routine, but one that had been thoroughly researched. Steak and eggs, high in protein and low in waste, so their bodies would handle long hours inside a sealed suit without problems. After that, doctors ran quick medical checks, listening to the heart, checking oxygen levels, making sure everything was normal. Then came the pressure suit, basically a life support system. Thick in some places, tight in others, connected with tubes for oxygen and cooling. Once the helmet went on and the visor locked, the outside world almost disappeared. Walking to the aircraft was slow because the pressure suit restricted every movement, with sweat forming before even reaching the cockpit. Once inside, the crew connected the hoses and sealed the canopy, cutting off the outside world. Only the sound of flowing oxygen and calm radio voices remained in the headset. When the engines started, the force was felt through the body, not just heard. On takeoff, the runway blurred and the ground fell away as the climb began. The blue sky slowly turned dark. The air became thin, the turbulence stopped, and the plane felt smooth and steady. Below, clouds looked like white oceans, and the earth grew quiet and small. At more than 80,000 feet, the horizon no longer looked flat. It curved clearly. The Earth's shape, something most people only see in pictures, was visible through the cockpit glass. Above it, the sky looked almost black, even with sunlight still present. Along the edge of the planet, a thin blue line glowed. That line was the atmosphere, the air layer that all life depends on. Seeing it so thin made it feel fragile, like it could disappear. Technically, the aircraft was still inside the atmosphere, since science defines space as higher up. But to the pilot's body, that difference did not matter. At that altitude, air pressure was so low that without protection, the liquids in the human body could begin to boil. The pressure suit and sealed cockpit were the only things keeping the crew alive. Even though they were not in space officially, the conditions were almost the same. The suit turned the pilot into a moving life support system. It provided oxygen, controlled temperature, and protected against extreme winds and heat at speeds over 3 times the speed of sound. Inside the cockpit, isolation was complete. The pilot could not feel wind or weather, only hear radio voices and system sounds. Movement was limited, and even drinking water meant using a tube. The plane flew where the human body could not survive on its own, forcing aviation to borrow from space technology. And this moment, when a pilot sits in a pressure suit at the edge of space, looking down at the fragile blue line around Earth, did not happen by luck. This plane in space experience came from one political disaster, one impossible deadline, and one group of engineers who chose to push human flight further than anyone ever planned to go. How a spy plane almost became a spacecraft. For years, people believed the story was already complete, but only recently have more files, pilot notes, and engineering records made it clear how extreme this aircraft really was. This was not just a fast Cold War spy plane. It was a machine that forced its creators to solve problems normally seen in space missions, while still pretending it was just another airplane. It flew so high that its crew needed life support systems, and it moved so fast that normal physics began to break down around it. How did a political embarrassment lead to a plane that lived at the edge of space? And how did a normal aircraft company suddenly start building something closer to a spacecraft than a jet? The story begins with a mistake the world watched happen. In 1960, a U-2 spy plane, flown by Francis Gary Powers, was shot down over the Soviet Union. The United States had been sending these planes over enemy territory to take secret photos, believing they flew too high to be touched. But Soviet missiles proved otherwise. Powers survived and was captured. The US government tried to say it was just a weather research flight, but the Soviets showed everyone the plane and its spy equipment. The lie collapsed, and the country was embarrassed in front of the entire world. It became clear that if one spy plane could be shot down, then the next one could be too. The US needed something completely different. Military planners now had 3 demands. The new plane had to fly higher than 80,000 feet, far above most missiles. It had to go faster than Mach 3, which means more than 3 times the speed of sound. And it had to be very hard to see on radar, which meant it needed a very small radar reflection. On paper, this sounded almost impossible. That is when Kelly Johnson and his Skunk Works team at Lockheed stepped in. Their group was small, intense, and worked under constant pressure, operating almost like a secret lab with locked doors and notes destroyed as soon as they were read. People only knew what they absolutely needed to know. Johnson promised that his team would design and build the aircraft in about 20 months, which many experts thought was unrealistic. The first version was called the A-12, and it would later lead to the Blackbird. So, how do you make a plane survive where normal planes would fail instantly? The team responded by changing almost everything about how planes were designed. The shape of the aircraft was the first major change. Instead of a round body and straight tail fins, it was shaped like a long dart. The vertical fins were tilted inward instead of standing straight up. The sides of the body were flattened, and sharp edges ran along the front of the wings and body. These edges, called chines, had 3 jobs. They helped create extra lift at high speeds. They helped make the plane more stable. And they helped break up radar signals so that less energy bounced back to enemy radar screens. Some areas of the plane also used early radar-absorbing materials, which helped reduce how visible it looked to tracking systems. Heat was an even bigger problem. At speeds above Mach 3, air rubbing against the plane creates extreme friction, and friction equals heat. The front parts of the aircraft could reach temperatures above 1,000 degrees Fahrenheit. Normal airplane metal, like aluminum, would weaken or even melt. So the engineers chose titanium. About 85% of the aircraft was made from titanium alloy. It was strong and could handle heat, but it was very hard to work with. If treated incorrectly, it could become brittle and crack. Many normal tools damaged it, so special tools had to be invented. Even the raw metal was difficult, because a lot of titanium delivered to the factory was rejected due to tiny amounts of contamination that could weaken the structure. Building this aircraft meant creating new methods just to shape and assemble the metal. People often find this part shocking. Why did such an advanced plane leak fuel all over the ground before takeoff? Well, it has to do with simple physics. The metal skin of the plane expanded when it got very hot during flight. So engineers designed the panels to be a little loose when the plane was cold on the ground. Once the aircraft reached high speed and heated up, the metal expanded and the gaps closed. Until that happened, fuel would drip out of small seams. This was not a mistake, but rather a side effect of designing for extreme conditions instead of normal ones. The engines were also unlike normal jet engines. The aircraft used Pratt & Whitney J58 engines. At takeoff and low speeds, they worked like regular jets, pulling in air, burning fuel, and pushing hot gases out the back. But at very high speeds, they acted more like ramjets. A ramjet uses the forward speed of the aircraft to compress incoming air instead of doing all the work inside the engine. This made the engine more efficient at Mach 3 than a normal jet could ever be. Controlling all that air at such speeds was extremely difficult. At the front of each engine, there were movable cones that slid forward and backward as the speed changed. These cones controlled how shock waves formed inside the intake. If these shock waves were not handled correctly, the engine could suddenly lose power, creating violent shaking. There were also internal doors that controlled how much air went into the main engine and how much bypassed it. Engineers had to carefully balance pressure, airflow, and temperature, or the entire system could fail. Fuel was another problem. Normal jet fuel would have been too dangerous at those temperatures. So a special fuel called JP7 was created. This fuel had a very high flash point, which means it was hard to ignite. In fact, a common demonstration showed that a lit match dropped into JP7 would go out instead of starting a fire. But this also meant the engines could not ignite it easily. So engineers used a chemical called triethylborane, or TEB. This chemical bursts into flame as soon as it touches air. Every time the engine needed to be started or the afterburner turned on, a small amount of TEB was injected, causing a quick green flash as it ignited the fuel. Each engine carried only a limited amount of TEB, so pilots had a limited number of guaranteed starts and afterburner ignitions on each mission. Could this plane ever operate without the people supporting it on the ground? Well, no, as it depended on a huge team. Each aircraft needed hundreds of trained technicians. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video.